Hello friends, welcome to EK lectures. In this lecture we will be discussing about the electric potential. Now let us understand what is the electric potential. What is electric potential? So in general the potential or the potential energy is the energy possessed by body, energy by body or a object due to the position with respect to a field, uh, any field. It can be gravitational field or electric field. Okay, so the potential energy is, if we have some field here, suppose the field increases from this point 0 and the field increases in this way. It can be either gravitational field or electric field, and if I place some object with the mass here, this object will possess some potential. This is a potential due to gravity. Now similarly, if there is some field, electric field, where the potential increases from 0 and up, and if I place some charge here it should be a object with some mass. Here there should be some object with some charge, so it will have potential energy. Okay, so due to its position, so if the charge is placed here, it will have higher potential energy because it is at higher potential. So potential energy is this. Now what about the potential? Potential is the position. Each position has some ability or property. From the ground, where there is zero potential or zero potential energy, if it get raised to some other point, increased, if its position is taken from zero potential to potential of some value here, it is raised to some point, some distance, then it gains potential energy. So potential is the point, the property of the point. Potential energy is when that particular body, object or charge occupies that position. Okay, so that is mean by the potential of the body. Now that's a small introduction to the potential. Now coming to the electric potential. Electric potential is uh, given, yeah, since it is potential terms such as energy, we can explain or understand the electric potential in terms of energy. So energy per charge, how much charge, or the uh, work done. This is better. what work done per charge. This is what is meant by the electric potential. Suppose we have a charge q here, and we have to find the potential of uh, this charge q at this position, at point P. So q, we have a charge, and at a distance, this is the point, at a distance r from q, we have to find out the potential. Now we know due to this charge q there is some electric field E associated with this charge q, and due to this charge q, somewhere at infinity, the uh, potential or the electric field is 0. And if I place a charge small q, it will experience 0 force or 0 electric field, because we know that force is equal to K capital Q small q by r square. If r is tending to infinity, F will tend to 0. So at infinity, the force is 0. It experiences 0 force. Now if the work is done, if I'm moving this charge from infinity to the point P, I have to do some work, because I'm doing the work against some force, because as the distance decreases, the force will increase. So work done can be written as work done equal to minus integral f dot dr. Now this minus indicates the work is done against the force. And from where to where? From the infinity to the point r. The work has to be done from infinity to point r. Now if we divide the work done, or the uh, work work done by charge q is equal to minus integral from infinity to r E dot dr. Now this work done by q is nothing but the potential V. Potential due to point charge. This is what we are going to do now. Potential due to point charge. Now as we have assumed, there is some q charge, and at a distance r, we are going to find the, at point P, we are going to find out the potential V. So V is equal to integral E dot dr minus with the from infinity to r. Now electric field is what we need. Electric field at point P at a distance r from Q is k q by r squared. So the potential V is equal to integral from minus integral infinity to r. Electric field is k capital Q by r square dr. Kq can be taken out. 1 by r square, integral is with the minus sign, so it is minus 1 by r from infinity to r. So uh, minus minus gets cancelled, so it's v is equal to kq into 1 by r from infinity to r. So putting the upper limit first, you have kq by kq into 1 by r minus 1 by infinity. So that's equal to kq by r. So this is the potential v of r for point charge. Electric potential due to circular ring. Now here this is the circular ring which carries charge q, and it has a radius equal to capital R, and at r distance from the center of this circular ring on its axis we have a point P, and this is where we have to find out the potential. Now the potential formula is V equal to integral, there's a minus sign, infinity to R E dot dr. Now electric field due to circular ring at a distance r is given by kqr divided by r square plus capital R square whole to the power 3 by 2. So this is the electric field at the point this here. Now we need to integrate. Now v is equal to minus integral from infinity to r. E is k capital Q r divided by r square plus capital R square whole to the power 3 by 2 dr. Now what we have is take the common terms, so minus kq integral r dr divided by r square plus capital R square whole to the power 3 by 2. This is from infinity to r. So this integral is so now the integral from integral r dr by r square plus capital R square whole to the power 3 by 2 is minus 1 divided by r square plus capital R square whole to the power 1 by 2. Now substituting that in v, we get, let's find v, we can minus infinity to sorry, so minus kq and minus 1 divided by r square plus capital R square whole to the power 1 by 2, and this limits are from infinity to r. Now substituting the so minus of minus, that will become plus. So substituting r square value first, that we will get kq into 1 divided by r square plus capital R square whole to the power 1 by 2 minus when r is equal to infinity, it is 0, so 0. So that's equal to kq by r square plus capital R square whole to the power 1 by 2. So that's the electric potential due to the circular ring. Find the potential due to circular disk at a point r distance from the center. The electric field at r is given as E is equal to sigma by 2 epsilon naught into 1 minus r divided by r square plus capital R square whole to the power 1 by 2. So this is the point where we have to find the potential from the circular disk. Okay. So now let's start with the formula for potential. That's equal to minus of integral from infinity to r e dr. Now the electric field is already given, that is mm, sigma by 2 epsilon naught with a minus sign. Within bracket you have integral from infinity to 0, sorry, infinity to r 1 dr. So dr minus integral from infinity to r dr divided by r square plus capital R square whole to the power 1 by 2. So this two integrals we need, so that's equal to minus sigma by 2 epsilon naught. The first integral says it's r minus the second integral is r dr divided by r square. So it's uh, when you look at this, the denominator, the derivative of the denominator is half into 2r, okay, 2 times. So integrating, what we get is 1 divided by 2 into uh, 2 times root r square plus capital R square whole to the power 1 by 2. Now that's equal to, that's from infinity to r. So that's equal to minus sigma by 2 epsilon naught into r minus r square plus capital R square whole to the power 1 by 2, and this is from infinity to r. So first putting the upper limit, that is r, you get minus sigma by 2 epsilon naught into uh, now let's rearrange these terms, r minus r square plus capital R square whole to the power 1 by 2. So this can be written as uh, let's once again write this, r minus r square plus capital R square whole to the power 1 by 2. Now here we need to expand this or substitute these values, put the limits now. So minus sigma by 2 epsilon naught, first the upper limit, r minus r square plus capital R square whole to the power 1 by 2 at r minus, now let's put the lower limit, that is infinity, that is r minus capital R small r square plus capital R square whole to the power 1 by 2 at uh, infinity. So this is what we need. Now the first term is when r is equal to r, so this terms remain. Now we need to check about the second term. So understanding the second term, r minus capital small r square plus capital R square whole to the power 1 by 2. Now using 1 plus x whole to the power 1 by 2 equal to 1 plus half x, we can rewrite this formula as r uh, let's write down this as 1 minus r into uh, so when you take r outside, this is half, so this will become 1 plus capital R square divided by small r square. So when you use this formula 1 plus x whole to the power 1 by 2, this becomes r minus r into 1 plus this is whole to the power 1 by 2. So 1 plus capital R square divided by 2 small r square. Now once again expanding this 1 r minus this is at infinity, so r plus uh, capital R square divided by 2r, so r minus r is 0, capital R square divided by 2r at infinity, this is also equal to 0. So the term what is remaining is only the r term will remain, the infinite term goes to 0. So now we have uh, minus sigma by 2 epsilon naught into r minus r square plus capital R square whole to the power 1 by 2. This is the potential V of R. Now to understand this formula, integral r dr divided by r square plus capital R square whole to the power 1 by 2. Now to understand this, let's take start from d by dx of root x. Derivative of root x is 1 by 2 root x, which means integral of this particular quantity 1 by 2 root x times dx will be equal to root x. So integral of dx by 2 root x is root x, which means integral of derivative of x, dx is nothing but the derivative of x, divided by 2 times root x equal to root x. So we have to write this equation, this integral, in the form of derivative of what is there in the denominator under the root. So here r square plus capital R square can be considered as x, which means dx equal to 2r dr. So in the numerator we have r dr, but 2 is not there, so we multiply the numerator by 2, so we get 2r dr, and since we have multiplied the numerator with 2, denominator also we have to uh, multiply. So integral of 2r dr divided by 2 root of r square plus capital R square will be equal to root of r square plus capital R square, because it is root of x, which is nothing but root x. X we have already taken as r square plus capital R squared. Okay, that's how the integral r dr divided by r square plus capital R square whole square becomes uh, r square plus capital R square whole to the power 1 by 2, or root of x. So that is integral r dr divided by r square plus capital R square whole to the power 1 by 2. For this hollow sphere, we are going to find the uh, potential inside on the sphere as well as outside. So let's start with V out. So V out equal to minus integral from infinity to R EdR. Now electric field outside due to a hollow sphere we have already seen, that is equal to K Q by R square. So substituting this value of E here, we get V out equal to minus integral from infinity to R K Q by R square dr. So that's equal to minus KQ by R with a minus sign again, minus 1 by R. So that's equal to KQ by R. So this is the potential outside. Now we need V on. So V on is V out at R equal to capital R. So what we get is KQ by R, that's equal to V on. This is V out. Now we need V in. So V in, if you want to find, minus integral from minus infinity to R E d R. Now assume that some point this is the infinity and it's coming from infinity to till this point. This is R equal to 0, starts from 0. This is capital R, and somewhere here we have infinity. From infinity to 0 you have electric field E out, and from infinity to R the electric field in this region is E out. From R to 0, from capital R, that is from the radius to R, the electric field is inside. So there are two electric fields, so we have to divide this or split this, that is minus integral from infinity to uh, capital R E out dr plus minus, then from capital R to somewhere here we have to find out the R, some point P. This is where we have to find out the electric potential. So from R to small r, E in dr. So that's equal to let's take the first term, minus from infinity to R, from infinity to R capital R, the E out we have already seen, that is KQ by R square, KQ by R square dr. So that's equal to KQ by R from infinity to capital R. So since 1 by infinity is 0, you will get KQ by capital R. So that's the first term. Now the second term, the minus integral R to small r E inside. So electric field inside the hollow sphere is 0, so 0 dr, so that accounts for 0. Now which implies that potential inside is equal to kq by r. So this is a constant value because k is constant, total charge q is constant, r is constant. So since v in is 0, electric field inside is, sorry, v in is constant, electric field inside is 0. Why electric field inside is 0? Electric field is equal to minus dv by dx. So my derivative of a constant is 0 because the potential is constant here. Here we have the solid sphere, and here we are going to find the the potential at point outside the sphere, on the sphere, as well as somewhere inside. Now before that, we'll just write down what are the electric field values. E out equal to k q by r squared. Then we have E on, that is kq by capital R square, and E in, electric field inside, is kqr by r cube, kqr by capital R cube. Now v out is equal to minus integral from infinity to z, let's write r, a point outside, so infinity to r, e out dr, so that's equal to minus integral kq by r square dr. This is from infinity to r, that's equal to kq by r from infinity to r, so that's kq by r. Now so we out, we have done, and then v in, so v in equal to minus integral from infinity to r e dr, since the value of e is different. So how it's coming from infinity to capital R, then to some point here, then r to small r, this distance is r. So the potential or the charge is coming from minus that is infinity to this point. So when it comes from infinity to this point, it has to undergo two different electric field. One is E out and another is E in. So from infinity to R we have E out dr, and from capital R to small r we have E in dr. So that's equal to minus k q by r square dr integral from infinity to capital R minus integral kqr divided by capital R cube dr from small r to capital R, sorry, capital R to small r. So that's the first term gives us kq by capital R minus this is minus kq by r cube, and r dr integral is r square by 2 from capital R to small r. So the first term is kq by capital R, then minus, so we will go with the lower limit first, so plus kq by r cube, this is 1 by 2. Put the lower limit first. Small r square becomes capital R square minus, now put the lower limit, so kq by capital R cube, so 1 by 2 into r square, so that's equal to kq by r plus, this is r square and r cube get cancelled, this becomes half kq by r minus kq r square by 2r cube. So this is kq by r, this is half kq by r, so this becomes 3 by 2 kq by r minus kq small r square divided by 2r cube. So this is the potential inside. Here we are dealing with the non-uniform charge distribution. For non-uniform charge distribution, we have a spherical charge distribution in this form. Spherical charge, okay, whose density rho of r is given as some constant times r, where r is the position from the center for r less than capital R, and 0 for, this is less than or equal to, and 0 for r greater than capital R. Now here first we need to find out the electric field E out. E out is equal to or E out into 4 pi r square. Applying the Gauss law, we have Q enclosed by epsilon naught, and from in the Q enclosed is rho dV, that's equal to integral, rho is CR r square dr integral sine theta d theta d phi. Now this is from 0 to capital R, and this is from theta is from 0 to pi, and phi is 0 to 2 pi. So this gives us C capital R power 4 by 4 into 4 pi, so that's equal to pi C R power 4. So this is the Q enclosed. So E out equal to Q enclosed is pi C R power 4 divided by 4 pi r square into epsilon naught, so 4 pi epsilon naught r square. Pi pi gets cancelled, so that is C r power 4 divided by 4 epsilon naught r square. So similarly, E inside equal to E inside into 4 pi small r square is it will become CR square. So pi C small r power 4 divided by epsilon naught, so that becomes that gives E inside equal to CR square by 4 epsilon naught. So this is the electric field inside. Now we need to find the potential out, that's equal to minus integral infinity to r E out, that is C r power 4 by 4 epsilon naught r square dr, and that's equal to cr power 4 by 4 epsilon naught 1 by r square integral is minus 1 by r, and that's from infinity to r, so that's equal to c r power 4 by 4 epsilon naught r. Here we have one more minus sign. So cr power 4 by 4 epsilon naught r, this is v out. So now v in equal to integral minus infinity to r e dr. Now to reach from minus infinity to r, there are two electric field, that is integral infinity to capital R e out dr, there's a minus sign, minus integral infinity to, sorry, this is capital R to small r e in dr, so that's equal to minus integral from infinity to small r e out. What's e out here? E out is cr power 4 by 4 epsilon naught r square, 4 epsilon naught r square dr minus integral from r capital R, this is capital R to small r, electric field inside is cr square by 4 epsilon naught dr, so that gives us the first term is let's write here cr power 4 by 4 epsilon naught, the minus sign, so 1 by r square integral is minus 1 by r from infinity to capital R minus cr square, so minus c by 4 epsilon naught, r square integral is r cube by 3 from capital R to small r, so this becomes c capital R cube by 4 epsilon naught minus here we have c by 4 or epsilon naught r cube by 3. Now put the lower limit first, so plus c capital R cube by 12 epsilon naught minus c small r cube by 12 epsilon naught. Now this is multiplied by 3 on both sides, here and here, so 3 plus 1 4, 4 by 12 4 by 12 is 1 by 3, so 1 by 3 cr cube by epsilon naught minus c small r cube by 12 epsilon naught, so this is v inside. Here the first term is a constant term. Here are some questions that you can practice. Find the potential V in, V out and V on the following spherical charge distributions, and here in each case rho of r is given. We have to find out first E out, E in and E on. On is not necessary, but E out and E in to calculate V out and V in.